My name is Daniela. I'm an electrical engineer employed at a company in the southern part of Germany. I'm doing software development and hardware development for a couple of centuries now. And I'm also a member of the C++ committee, in particular in the evolution working group and in the tooling group. This is the stuff that I'm mostly interested in. So, for the motivation of this talk. This is an experiment, because every time I read something about C++ in the social media, I experience some very vocal people about spreading defects on C++. Like, C++ is dead, go to Rust, go or whatever. Or like, the committee cares only about the nerds. Or the committee cares only about the library developers. For us mere application developers, there's no love from the committee. Or usually the committee is too slow and doesn't deliver anything that it needs. Or even more so, the committee is too fast and we can't keep up with all the new stuff. Just slow down a little and think a little bit more about what we are bringing each 3 years. And you can even read comments like that. The committee is just a bureaucratic bunch of morons, completely detached from reality. Forget about all this stuff. And some people say C++ or free is all you need. Everything else is just syntactic sugar. You don't need all this stuff. So I thought, I have a different opinion, but is this actually true? Let's try it. Okay, what did I do? A reality check. Well, as you heard, I'm about 40 years in software development, so I can't put my shoes on like a beginner or a much less experienced developer. But I can at least try to do something that I've never have been done before, like possibly using some completely new language features or completely new libraries that I'm not experienced in, or I can use some stuff that I probably have been doing maybe in the past couple of weeks at my company or something like that. And I tried to make them work together in a way that you think, yeah, this fits together. And this is the reason why I'm talking about contemporary C++ in action. But first, what do I mean with contemporary C++? Is it the ancient but proven C++ 98 or 3? Probably not. But what about the Renaissance, the second birth of C++ in C++ 11 and C++ 14? Maybe it's that. Or what about C++ 17, where we got all the nice new pieces, nothing big, but all the nuts and bolts that we used every day to create our applications? Or is it the big bang of C++ 20 with all the big new features that we have never thought it would be such kind of crazy and amazing stuff that C++ 20 has given us? Or maybe just the latest one, C++ 23, it's in the making. In my opinion, it's all of that. All the pieces that are proven to work, that fit together and make our lives as developers much better. And what about the other half of my title, in action? As I've told before, I'm an engineer and I'm presenting a demo application that should contain all the engineering kind of stuff that I deal with in my work every day, and this for a decade now. Data collection, data processing, data visualization, near real-time networking, library usage, library creation if you have to, designing good interfaces, and I take advantage of everything that I can take of. Whatever it takes, I will use it in my demo application. These pictures you have seen, this is the kind of work I'm doing every day. So, let's talk about the specification of the application that I will be showing you today, and then I switch over to the demo code. But as an engineer, first, before I do anything, I need a specification. The specification is like this. The application will have a server, it will have a client, and the server waits for clients to connect, and to do that, it sets up a list of endpoints that you can give from the command line, and then the client connects. The server part will look at a given directory for media files, in particular GIF files with media content in it. It will decode each of these files into individual video frames, and after decoding, it will send the video frames at the correct time to the client. And if there happen to be no video frames to produce, maybe the directory is empty or it doesn't even exist, then the server will send filler frames to the client. The client will try to connect to one of the endpoints of the server. It will receive these video frames from the network connection, and it will present the video frames in a GUI. And the whole application is supposed to be robust against failures or problems in the networking or whatever it might take. It is quite typical in industrial applications that you have to be prepared for networking failures and this kind of thing. And the applications that do quite the same. And this means I have to handle timeouts and errors, and the whole application should be brought down in an orderly manner, no matter what. So here's the specification once again. And as you can see, it will come down to at least 5 major parts of the code that I have to implement. I have to implement some kind of networking. I have to implement the server. I have to implement a GUI. I have to implement the client code. And I have to implement some kind of user interaction so that the user can interact, making the window larger or shut it down and all this kind of things that you want from a good GUI. And let's start with the biggest part, and this is the server. But there's a thing. To actually serve anything, I have to decode my video frames. How should I do that? So I implemented a module. This is called Video Decoder. And this module Video Decoder implements exactly one function that's exported from the module. This is called make frames. It gets a directory path where to look at, and it generates video frames, as you can see from the return type here. If you're not familiar with generators, generator is a kind of an interface in front of a coroutine that gives you the a facade to iterate over all the particular entities that are created within the coroutine. And every time you do a next iteration step, it will create a new video frame for you. So let's look at the implementation. The actual implementation will be done using a third-party library that is called libav. If you're not familiar with it, maybe it's more known under the name ffmpeg. ffmpeg is driven by this library. It's just the front end, the ffmpeg kind of thing. So the module video decoder will use this particular library libav, and this library itself is also compiled into a module. I've created a module out of the whole libav library and just imported here. Instead of individual headers from the library, I bring in the whole library at once using this import here. I'm using ranges and I'm using views, so I have made a short namespace alias for it just to make it more palatable to you. And as you probably know, this libav library is a C library, and we are C++ developers. We can do better. We can wrap all these structures and constructor functions and destructor functions implemented in C style and wrap it into proper C++ types, and I have written a resource wrapper that does all this kind of thing to make it more palatable. The interface of the wrapper is modeled after a unique pointer, but on top of that I have two more template arguments. The first one is the constructor function from the C library, and the second one is the destructor function from the C library. And this triple together make it much more easier to handle all this C kind of stuff. And with that, let's look at the pipeline to decode the individual video frames. As I said, I have a directory which I give to the video decoder, which contains or is supposed to contain GIF files with videos in it. And the specification says I should iterate over and over endlessly. This is an infinite stream of video files that I'm going to process. So I have an directory iterator, just like the file system iterator, but it's wrapped in a way that every time that the directory iterator has come to an end, I will just start over again. So I get an endless stream of file paths out of this iterator. And because I have made it such a way that all these four concepts here, iterator, range, viewable range, and borrowed range, is satisfied by the implementation of this iterator, I can use it in any settings that I really like. If you're interested in, they can show a little bit later on how it's actually done, but it's quite easy. Then every time I do an iterate step using this iterator, I have a view pipeline constructed here that processes all the paths that are created from this iterator. First, I try to filter it based on metadata, looking at just the extension. So this filter has a implementation that takes just one of these paths, looks at the extension, and if it doesn't match, it will return false, such that the view pipeline will filter out improper paths from the iterator. Next, after I have at least paths that look like containing video files, I'm going to transform it in 2 steps. The first one, I'm trying to open the file and let the library look at the contents, if it's really a GIF file and if it's really a video file. And in the second part, then the libav library says, yeah, this sounds great. I can actually do something with this given file. I will provide you a decoder just to decode the video streams, the encoded video stream, into individual video frames. And with that in place, I can then use a range-based for loop, take out one file with an associated decoder, and do something with it. If the decoder happens to have actually video frames in it that it can produce, then I will go and decode each of these frames and yield every one of these frames using this generator interface to the caller of this function. And if I don't have a decoder that I can use, maybe the path was not sufficient or the contents were not correct, I just yield a filler frame. So both of these CO yields will return the produced video frames using this generator interface here to make it easy to use this coroutine in the surrounding code. And this decode frame coroutine here itself is a generator with a coroutine inside of it. Here you see a loop nest that reads the frames, sends it to the decoder, and each time the decoder spits out a decoded video frame, I make a structure out of it that I can send over the network to the client. So here, this function make video frame just takes some properties from the decoder, like the width and the height of the video frame, the line size, such as the amount of bytes along a line of video, a video format, because you can have different orderings, RGB, pixels, and a sequence number, and a timestamp, and this is important, a timestamp. And on top of that, not only this kind of header, but also a bunch of bytes that take all the individual pixels that are come decoded out of the libav decoder, and this is then the stuff that I will be sending over to the client. So, with that in place, I can have a slight peek at these 2 transformation functions. The first one was opening the file, the other one was trying to find a decoder. You see, this is really small code put into an individual function just to do one piece of the step here to arrive at the processing of encoded frames into individual video frames. So now we have our video frames available at the generator interface. Here, I can send them out to the client using my server. So let's look at the server part. The server is using a library called ASIO. I don't know if anybody here is familiar with ASIO, probably Boost ASIO. It's an asynchronous framework, and it contains a lot of networking functions that you can use to asynchronously receive or send chunks of data over Ethernet net connections. It can create acceptors, everything that you need to do actual networking over Ethernet. And I've also created a module out of this ASIO library so that I don't have to bring each and every single header of the ASIO library in here. Everything is placed in this module ASIO, which is pre-compiled and ready to use. This ASIO library is, I don't know if you have ever worked with this library, it's really annoying with all these callback kind of things that's going to be used. You have every single operation has a callback when the asynchronous operation finishes, and with each callback you have to implement a piece of a state machine, and everything is scattered around your source code, so it's really, really hard to reason about this networking code that you're going to implement, and in particular, it's really, really difficult to handle problems. If you have a problem like a timeout or somebody has pulled the cable out of the networking interface, to really handle this kind of problems is difficult, really difficult. So to cope with this kind of problems, I have some additional pieces of code here. In particular, I have made the data types and the objects that you can use from the ASIO library into a more palatable interface, and this uses coroutines again. Here I have a type factory that says every time you have a socket or every time you have an acceptor or a timer, do not use it with this kind of callback functions, but tell the ASIO library that it should return everything through a coroutine interface. Bring it through an awaitable that you can co-await on. And even better, this ASIO library has a coroutine operator where you can compose individual asynchronous operations. And for example, you can say you have a socket where you can await reception of a data stream, and you have a timer that you can actually tell, okay, this reception of data should take no longer than maybe 2 seconds. Then you can compose it into a combined coroutine, And then either one of these both operations finish, the other one will be cancelled, and there's just one return that is actually produced from this operator. The only problem here is it returns an variant of tuples. This is not really nice to use. So I've created an adapter to make it so that every of my networking operations will return an expected. Expected is one of the new C++23 things that make probably life much more easy, because you're not only returning the data type that you are looking for, but you can also, if something goes wrong, bring a good reason and a description about what's going wrong, what's the disappointment that you're dealing with. In this particular part, the data type that I'm using to describe the disappointment, the kind of failure, is just a std error code. So everything in the networking interface is using these expecteds here as a return type, just to make it much more easier to use them. And with that in place, I can go back to my main function, and here I have 4 basic networking operations that I'm gonna use. There's one using, it's called send. It takes a socket and a timer and the data what I want to send. And if you look at the implementation, it's just an async write and timer wait using this operator to compose this one into a single coroutine that I can await, then adapt it here and return an expected type with either the expected kind of data. In this particular case, it's just the amount of data that has been sent over the network. And in case something failed, I get the appropriate error code. The same is going on here in the receive from, just the same socket, timer, and a buffer that I've been providing that needs to be completely filled. Here, once again, an asynchronous read, an asynchronous timer wait, and just get an expected out of it. And there's another one, a connect operation, just the same here. But this time I'm taking a list of endpoints that I want to connect to, plus a timer once again. And here I'm also composing these individual asynchronous operations into a single one with mutual cancellation. So here in this particular part, I get either an open socket or I return the error code through the unexpected channel of the expected data type. And the last thing here is a close operation, but this is not as interesting. As a helper function, I have a resolver that you can use to get a host name and a port number and a timeout, and it will come up with a list of endpoints that I can use. So, with this in place, let's finally come to the server itself. The server itself is just a single function. The function takes a context and a stop source. We will come back to the stop source a little bit later. It takes up a list of endpoints and, of course, the path to the directory that we are going to observe. What it's doing, for each endpoint, it tries to create an TCP/IP acceptor, and this acceptor is nothing else but a piece of work that's going to be scheduled on the work queue that ASIO is, as an asynchronous framework is providing us. So yesterday maybe you've been to the talk from Bryce about the sender-receiver framework. This is just the same here, but it's much more an earlier design from the beginning of the 2000s, but the sender-receiver is, from the concept here, quite the same. You have an asynchronous framework, you have to compose the kind of stuff here, and the ASIO library is just implementing the same kind of thing, just with a different vocabulary. So what I'm going to do is I call a coroutine and schedule it here using the CO spawn function onto this work queue provided by the asynchronous library. And notice here I'm creating an object that is part of the function parameters of the accept coroutine here. So it lives on the coroutine frame that's generated from the compiler. And as long as this acceptor is open, I can then wait for incoming connections and spawn new coroutines. With every connection that's coming in, I spawn a new coroutine. This is doing the streaming part. And this streaming coroutine is actually doing the decoding work and sending the stuff over the network. It gets the connection, the socket and the source, and using the generator from the make frames function that I've been showing before, this stuff becomes really, really simple. It's just a range base 4 over the generated video frames. It waits for the exact time, then it should send out the duly decoded frame to the network, composes two buffers, one for the header and one for the pixels, and sends it out here, send to the function that I've been creating before, and sends it out to the network. If anything goes wrong, or the user has requested a stop, the coroutine will stop doing its work and will just finish. So, as you may have seen, there's a question? The question was if the send buffers are combined before transmitting. Yes, this is part of the ASIO library. It will take a gather list of individual buffers and does whatever needed to send it out over the network using all the correct sized TCP packets. So you don't have to deal with that. It's just everything implemented already within the ASIO framework. More questions about this particular piece? Okay, so what I want to point out here, as you can see, everything is implemented as a coroutine except for the initial serve function. This gives us two major benefits. The coroutines, as implemented here, are strictly nested with their lifetimes within the calling coroutine. Everything that has to live long enough has bound its lifetime to the coroutine frame, so that if I use the socket here from the parameter, or the timer that is created here, strictly within the lifetime of the coroutine. So I don't have to create new objects like sockets or whatever it might be, I just can, the send-to function can just borrow these resources without fearing any lifetime issues in this particular case. So using coroutines can be a good measure to deal with all the lifetime issues that you can run into using asynchronous operations. And this is just one of the major benefits of using coroutines here in this case. You may also notice there is not a single global object or something that you can have to put into a class. Typically, if you implement a server, you have a class that does the implementation for you. This is just nested functions. There's nothing more to it. And so if you think about it, if you want to serve not only using one thread, you can have as many threads as you like. You can spawn many of these coroutines in parallel. Nothing is shared in here. And this is a really major benefit of having all these resources that you need to implement this video pipeline, these acceptors, these send functions. Everything is nested and using just local resources. Nothing more is needed here. And this is quite different from what you typically see in server implementations. Oh, I see there's a question over there. The question is, this logical OR operator here from the ASIO framework is similar to the sender-receiver algorithms that Bryce has been presenting yesterday. It's right, the observation, this is just the same as, how was it called? When any, yeah. And this is just the same functionality here. And I think using this kind of operator is quite simple to understand. Either this operation succeeds or the other one, or if any of these produces a result at the coroutine interface, it will cancel the other, and so the combined result will return to the core weight of the caller. Any more questions on that? Okay, let's move on. So I have shown the implementation of the server, of the video pipeline, and now we can move on. Oh no, that's not this kind of thing. To the other parts. I need a GUI. What kind of GUI can I use? It's just a small application. I decided to go with the SDL2 to be precise. I've also made it a module because we learned yesterday from Phil, we compile everything ourselves. This is what I did. I compiled the SDL into a module, and I'm going to use it. Okay, this is not that terribly interesting. I'm just wrapping the C functions from the SDL into C++ entities that I can use easily, and the GUI is a structure using a window, a renderer, and a texture that I'm going to use to implement my GUI. yeah, I can create such a window with given sizes. I can update it from a video frame just to accommodate to the actual size that I'm going to need to present an individual video frame. I can present the pixels on top of it, and I can process the user events that come in from the interaction with this window. This is all I need, and with this GUI in place, I can implement the client. The client uses just the same functions from the networking layer that I've been presenting before. And as you may already see here, the client is just as well a coroutine. It takes the endpoints that I want to listen it to and the GUI. And first it tries to connect to any of these given endpoints. And if it succeeds, it will play all the video frames that are coming over the network connection to the GUI here. And the video frames, first you need to receive the header just to know what amount of pixel data you have to expect. If the video header tells me I've need this amount of pixels that I have to present, it asks a memory resource, this is called pixel space here, to provide enough buffer space to put all the received pixels in here. And then it has received a frame. It can update the GUI according to the new sizes that may have changed and present the pixels on top of it. And with each received video frames, it will also put a log message onto the console using this new C++23 feature called print. And this is not implemented in any library that I'm aware of, but I've made my own standard library. It's implemented in here, so I can use it. The actual receive code for each individual video frame is extremely simple. I provide a space just large enough for the header, properly aligned, of course. I await the reception of the right amount of data from the networking interface, and if I get it, I bring the header object back to life, because before it has been just the raw bytes, the object representation, but I don't want to have UB. I in place new the header, and now I have a properly living object at the correct place that I can interact with and ask for for example, for the header size, get the right amount of bytes and receive the pixels from the network and put it then back together into a complete video frame, take the header and the pixels. This is all it takes, and just bring it through the available interface to the caller. Here we have just the same kind of construction, strictly nested coroutines within each other. I can lend my resources to the nested coroutines within and reuse them properly. So everything is there. I have the server, I have the video decoder pipeline, I have my client, just a little bit helper code here for the user interaction. I can wait on a SIG-term signal, and I can also wait on maybe a close from the window. This is not too interesting here, just two more coroutines. Now let's bring all of this together and let's try to compile the whole application. Here I have a command line parser that I've taken out of our company code base. I get a media directory that I look for TIFF files, and I get the server name. If there is no such path to the directory that I just bail out, the same I try to find out the server endpoints with the given server name and the server port. And if there are none of them, I just stop as well. And here are the pieces that hold everything together. I have an Ico Io Context, which is the representation of this work queue. This work queue is where everything is going to be scheduled on. My coroutines that I've implemented myself, and all of the callbacks that are coming from the asynchronous networking interface. Everything is scheduled on this particular work queue provided by the ASIO framework. And this is something that I've been skipping over throughout the whole of my talk so far. I'm using a C++ 20 feature called stop source. And now, I don't know if you're familiar with stop sources. I think it's just a great idea to give all the pieces of your code that you have and the job running completely separate from everything else, the signal to properly shut down. And this shutdown is being initiated either from the SIG term that I've been waiting on, or it's from the user interface that I've been waiting on, or it's from any of these networking errors that I can experience during the reception of the video frames. In all of these kinds of things, I have, no, there's not this one here, but this one. In all of these cases, I'm bringing in here the stop source, and if the signal is sent, or if the GUI just says, okay, let's stop the application, at the end, it says stop, request stop, and all the other parts are just brought down. Because you may have noticed every one of these coroutines here, let's look, for example, on the client, has a copy of the stop source here that will then trigger a callback local to the coroutine and closes all the objects that I have here. For example, it closes the sockets, closes the acceptors, it cancels all the ongoing networking operations. So just by listening and local reasoning about what's going on here and bringing down all the resources local at the same scope where the resources are living in, I have a clean and proper shutdown of everything without doing anything else besides listening to this kind of stop sources. So with the work queue here and the stop source, I can then here start serving. This is the call to the server. I create a GUI. I spawn my observers for the signals, and I also spawn the coroutine to show my video frames. Everything is just an individually running coroutine on this work queue provided by ASIO. So let's look if it really compiles. this is the build system. Just can't flush. Okay, let's rebuild it. It should hopefully work now. No space left on device. Okay. So it compiled, but it doesn't do anything. The return code 0 tells me everything is fine. Nothing is going on here. What has happened? Has anybody a clue? No, there are GIFs. Exactly. I've just scheduled all the work on the work queue, but I didn't make it run. So let's make it run. There's one thing, one line that's still needed here. I have to connect my work queue with an actual execution thread. This is what this statement is doing. I'm connecting the work queue to the main thread of execution. Compile it once again. Does it work? I think so. If you use the proper language features, if you use proper libraries, wrap them as much as you need to use them in your code, you can have simple code. Maybe you've seen the inner part of the video pipeline and the inner part of the server. It was just small, simple to understand code. It is concise. Everything does exactly what the functions or the coroutines are telling us from the names. This code is safe. There are no lifetime issues here. There's no data sharing here. You can fan it out into as many concurrently executing threads as you like. It is composable. I've brought many different parts, different libraries, different self-written functions, and all of this stuff is composing in such a way that it just works. And I think this is really beautiful. And with this kind of structure, your code is probably really enjoyable. You don't run into too much troubles. You don't have to think about all this stuff that you typically have if you have parallel executing code or lifetime or something, all this kind of stuff that you don't want to see in your daily life, and this is so hard to debug. Just by proper construction of your code, you can totally avoid all of that. So, some more resources here. The demo code is on GitHub. You can find it there. I will publish an update to that with all the latest changes that I did while I was here at the conference. And you can see all the information from the committee, like the papers, like the current draft of the C++20 standard. You can also see the implementation status from the different compilers. I've been using Visual Studio here because it has many, many features that are required, but I think most of the stuff, or even all of it, can be done also on Clang and GCC. There are some channels that you can reach out to me if you have any questions, besides the whole track, of course. And with that, I'm done with all the material, what I wanted to present to you. And if you have any further questions, please feel free to raise them.